In order to compare rational and irrational numbers, we need to express the numbers in similar forms. Since an irrational number cannot be expressed as a ratio, we need to express the numbers in decimal form in order to compare them. This is also problematic since irrational numbers, when expressed in decimal form, never terminate and never repeat. So, any decimal representation of an irrational number is an approximation rather than an exact value, which can make it difficult to compare with another value. How specific the approximation should be will depend on how precise we want to be when comparing values. Which is greater, square root of 14 or 4? Which is greater, square root of 2 or 1.3? Which is greater, square root of 90 or 9.485? If we were simply trying to determine between what two integers a square root lies, for example, between what two integers does the square root of 8 lie, we could simply identify the two closest perfect squares to 8. The closest perfect square less than 8 is 4, and the closest perfect square greater than 8 is 9. When we take the square root of these two numbers, we find that the square root of 8 lies between the integers 2 and 3, closer to 3 than 2, since 8 is closer to 9 than it is to 4. If we wanted to be more specific, we could look more closely at the differences between the perfect squares and 8. 4 is 4 units less than 8, while 9 is 1 unit greater than 8. To approximate the decimal to the nearest tenth, make a fraction from the difference between the lower perfect square and 8. Place this over the total difference between the two perfect squares and convert it to a decimal. Add this decimal to the square root of the lower perfect square to find that the square root of 8 is approximately 2.8. This method will usually yield an approximation accurate up to 1 decimal place. If we want a closer approximation accurate to 3 decimal places, we can use a simplified version of a method developed by Sir Isaac Newton, known as Newton's method. This method begins with an estimation of the square root e, dividing it into the number n, whose square root we are approximating, adding the original estimate to this quotient, and taking 1/2 the sum. As is evident when we look at the equation behind this method, it basically takes two estimates, one below and one above the desired approximation, and averages the two to arrive at a more accurate estimation. If we use the approximation to the nearest tenth for the first estimation, we can achieve an approximation accurate up to 3 decimal places. This equation can be used repeatedly to achieve successively more accurate approximations. Let's see what happens when we use Newton's method for one more approximation. Using a calculator, we would find that the square root of 8 approximately equals 2.8284271. The estimate was accurate to 7 decimal places. Do you know why Newton's method, when used over and over, will result in increasingly more accurate approximations of the square root of a number? As mentioned before, e and n divided by e will always lie on opposite sides of the number whose square root we are approximating. So when we average them, we get a closer approximation of the square root. When we use this method repeatedly, we are achieving successively more accurate approximations. One important note: Although any number can be used for the initial estimation, the more accurate your first estimation is, the quicker this method will take you to an approximation that is accurate to the desired number of decimal places. Since we used our approximation to the nearest tenth for our first estimation, we were able to achieve an approximation accurate to 7 decimal places in just 2 tries.